Hello. So today we're finally going to be talking a little bit more about trying to apply mass balances to this pesky issue of reactors. So we're going to be focusing on our one special case of mass balances, and that's more or less what happens when I feed reactants into reactor. Because at this point, we've got a slight issue because my products and reactants aren't the same. So we're going to have to change the notion of how we perform balances. Because turns out number of molecules entering the system, not necessarily the number of molecules leaving the system. So what we end up having to do is back up to in the older mass balance we were using. So previously we dropped out the generation and consumption terms with our mass balances. We're gonna have to use those again. So I can no longer essentially just say that inputs and outputs are gonna be set equal to each other because the identity, the amount of each component can be changing as I may end up generating products and consume reactants, and intermediates are their own special ball of fun. So, also due to this fact, we're going to want to stop using mass as our key unit and focus a little bit more on moles and molar fluxes. But watch out because it's still pretty common that you're going to see masses used when describing reactive systems. So you're going to need to take a pause to do a little bit more math. So let's go ahead and work this for an example system. So let's say that I've got the good old case of combustion. I'm feeding in methane and air, which is going to be a mix of O2 and N2, and I'm going to end up producing a whole slew of products: methane, CO2, uh, O2, N2, and water. And I'm going to be doing this at a 95% conversion rate. And now I need to try and figure out what the rate of production of each of these products are. So, as a chemist, here's the question. How would I solve this problem? So, simple approach. I pretty much take my initial numbers, turn them into molar flows, set up an ice table, solve the system, maybe use a more advanced technique. As an industrial chemist, we're going to kind of flip the notation, and I'm going to tend to use mass balance. But here's the thing, we actually have two different choices of mass balance to use, which we're going to cover in the subsequent two lectures. The first of which is going to be molecular balance. So in this case, I'm going to be using input plus generation equals output plus consumption for each of the 5 molecules involved. So this is going to require solving a whole bunch of serial equations, as each equation will give me a little bit more information I need to solve the subsequent molecule. The alternative is going to be to use atomic balance. So what I'm going to do is convert from moles of each of these molecules of O2, N2, and H2, and turn this to the moles of the individual component atoms: carbon, hydrogen, oxygen, nitrogen. And I'm going to balance each of these sub-elements and then convert back, use input equals output, because I can't change unless I've got a nuclear reactor. Those aren't changing. And then convert the moles of atoms back to the moles of molecules at the end. So these topics are a little bit involved, so we're going to solve each one independently in the next two lectures. Till then, take care.